Hello, everyone. Thank you for joining us today. My name is Gavin Jenkins, Managing Editor of Roads and Bridges Media. On behalf of Roads and Bridges and our sponsor, MAPEI, I'd like to welcome you to today's presentation titled Corrosion Mitigation of Traditionally Reinforced Concrete Structures. In this webinar, we will discuss MAPEI Corporation's vast array of corrosion mitigation and prevention materials and how to confidently determine which technology is best suited to a given application and ensure the longest lasting repair option to choose. Being able to select the most appropriate technology and/or product ensures the owner gets the longest lasting repair at the most efficient cost, ensuring future repairs and impact on traffic are minimized. We're going to get started in just a couple of minutes, but first a little housekeeping. You will notice on your viewer that you have the ability to ask questions. We encourage you to ask questions, and we will try to answer as many as we can at the end of the presentation based on time availability. Any questions we do not get to, we will answer offline. Today, our presenter is Brian Stratman. Brian Stratman is a professional engineer, and he is the business development leader for corrosion and structural strengthening with MAPEI Corporation. Brian's work experience includes structural design of commercial and retail structures, territory sales manager for power and industrial concrete repairs and grouting, business development manager for steel piling, fiber reinforced polymer strengthening, and corrosion mitigation. In his current role, Brian is responsible for business development and engineering support related to MAPEI's structural and strengthening and corrosion product lines. He has over a decade of experience related to the design and installation of FRP strengthening systems for concrete and masonry structures, and is also an NACE certified cathodic protection technician. Brian is also an active member of the ACI 440 Strengthening Committee and ICRI Strengthening and Corrosion Committees. And with that, I will turn it over to Brian. Brian, the floor is yours.
All right, thank you, and good afternoon, everyone. I guess good morning if you're on the West Coast. So I certainly thank you for taking some time out of your day to learn about corrosion this afternoon. So I'll get right into it. We are going to be talking about corrosion mitigation of concrete structures, what is today's topic. So with that, there we go. With that, we just have a few kind of different objectives that we're going to go through. We'll start out, if we're going to talk about corrosion, unfortunately, we do have to talk about a little bit of chemistry. I'll freely admit it's not my favorite subject, but it is good to have a basic, understanding of what's happening. We're not certainly going to be getting into anything too crazy or, and getting your textbooks out or anything like that, but just have a, fundamental knowledge of what's happening in the reinforcing steel and the concrete. So you understand how these products and technologies work to affect the corrosion in the concrete. So we'll learn how to kind of assess what the causes may be and the different effects that you might see from different types of corrosion. And then in the latter half of the presentation, we're going to go through some of the different technologies that are out there that you can use for mitigating this problem that is pretty typical of concrete structures around the world. So with that, we'll move forward here. So the causes of corrosion in concrete, it's really at a basic level, it's a change in the chemical environment of the concrete. So either you're adding something like chlorides. So, I live in the northern part of the United States. We're certainly in the wintertime adding a bunch of road salt all over the place. Road salts, of course, include chlorides. So we're adding a lot of chlorides to the surface of our concrete as it cracks and spalls. And, we get freeze thaw and melting of the ice, and the water starts infiltrating into the concrete. You get chlorides into the concrete. Down in the southern part of the country along the coastal areas, it's not obviously a road salt problem. It's a lot warmer down there, but they do get airborne chlorides from the ocean. So, as the ocean spray comes into the coastline, it actually penetrates quite far, as we'll see. It's not just an issue, a couple feet into the coastline. It's actually several hundred miles inland from the coast that you get airborne chloride. So really, what we'll be mostly talking about today is chloride-induced corrosion, because that's really probably 90% of the time what we're dealing with in concrete anyhow. We'll also touch on a subject called carbonation, which is something that happens right after concrete is mixed. So we'll go through that as well. That kind of causes more widespread corrosion. It's not like a pitting type of corrosion that chlorides cause, so it's not of as much concern, but it does actually accelerate the chloride-induced corrosion, as we'll see moving forward. And then the other third option that could cause corrosion, it would be chemical attack. This would be more typical of, let's say, a chemical plant or maybe a wastewater treatment facility, places like that where you have big tanks or concrete tanks where you're filling it up with chemical laden water or waste, whatever it may be. So again, that's more of a specialized area. The concepts are really the same. It's just a different chemical. So chloride-induced corrosion is very similar to chemical-induced corrosion. It's obviously just a different chemical, but we're really not going to spend too much time discussing that today, just because really chlorides are really the most common cause that we're running into in the concrete industry. So when we pour fresh concrete, it's pretty typical. You build a new structure, bridge, whatever it may be, out of concrete. It looks pretty nice for the first 10, 15, even 20 years. Oftentimes, you don't see the spalling and the cracking that's indicative of some of these older structures. The reason that happens is when you pour fresh concrete, there's something that called the passivation layer that forms around the reinforcement steel. You can kind of think of the passivation layers being similar to like insulation around a electrical wire. It's basically just a sheathing that forms. It's an invisible sheathing. It's not like an actual coating that you could pull off or see, but it's basically a chemical coating that forms around the steel and basically prevents the chlorides from reacting with the iron and the reinforcing steel. So as long as that passivation layer remains in place, chloride-induced corrosion simply cannot happen. It's just chemically impossible. The reactions don't happen. If the reactions don't happen, then obviously we don't have corrosion. The trouble is the passivation layer eventually is going to be breached. There's a couple of different ways that it can be breached. The first is via an influx of chloride ions. So different textbooks will have different numbers for what the exact number is, but generally it's around 300 to 350 parts per million of chloride concentration is sufficient to penetrate the passivation of reinforcing steel. So we're talking pennies difference here between 300 and 350 parts per million. It's not a lot. So you'll just see different numbers in different places. But the end result is really the same. So as you get more and more chlorides, start accumulating in your concrete, again, from that road salt, from the ocean spray, whatever it may be, those chlorides start to accumulate around the reinforcing steel. They want to react with that iron. The passivation layer works to protect the iron from reacting with it to an extent. But when you get above this chloride ion concentration, then the iron in the reinforcement steel is able to actually start reacting with the chlorides. Once that happens, then of course corrosion starts to occur, and we start to see the cracking and the spalling and the rusting and all the other problems that we associate with corrosion of reinforcing steel. Excuse me. The other cause or manner of which the passivation layer can be breached is through a loss of alkalinity of the concrete. So when we first mix concrete up, it's pretty high pH, so it's not uncommon to see a pH of 12, 12.5, even 13 of freshly mixed concrete. However, as carbonation occurs, which we're going to talk about here in the next couple of slides, that pH starts to drop. So you start to get more of a balanced condition with the environment around the concrete. pH comes down, and once it gets below 10, the passivation layer can be breached. So this isn't a combination thing. So the passivation layer could be breached either by the chloride ions or by a drop of alkalinity. So if you only have, say, 100 parts per million of chlorides in your concrete, but the pH has dropped all the way to, say, 9.5, those, the 150 parts per million of chlorides will actually start reacting with the iron at that point because the pH has dropped. So one of these two things is going to happen first. And it's really just a matter of time. In most cases, it's really impossible to prevent the chlorides from, being placed into the structure, either along the coastal areas. Obviously, the ocean spray is not something we can turn off. And until we find something better than road salt for melting ice on the roads, we're going to keep dumping chlorides up in the northern areas as well. But once the corrosion starts happening, now you have chlorides that are able to actually start reacting with the iron in the reinforcing steel. The passivation layer gets breached, and those chlorides really start to react with iron, and they start forming what we call iron oxides. Iron oxide is the technical term for rust that you're more familiar with. So that's the orange, rust color that you see kind of leaking out of the concrete. And of course, the rust that you see on the reinforcement steel. That's from the formulation of those irons reacting with oxygen. And again, we'll go through this more detail here in the next few slides, but just as an introduction to what's happening. So the carbonation, we're going to kind of step backwards just for a minute here and explain what's happening with the carbonation. So Portland cement has a high amount of calcium hydroxide in the cement. That's just part of what makes cement. It has calcium in it. Calcium reacts with hydroxides and the air that's around it. So basically water and air, and it forms what we call calcium carbonate. So calcium carbonate actually is in some instances is actually good for the concrete. So the calcium carbonate, it kind of fills in the void spaces in the concrete. So it makes it a more dense concrete, which actually would increase the compressive capacity of the concrete. So on the surface, it seems kind of like a good thing, but as we'll see, it causes a drop in the pH. So even though you do get some marginal increase in the compressive strength, its ultimate effect is dropping that pH, which is of course not a good thing. But this happens really immediately. There's nothing we can really do about it unless you could somehow prevent air from coming into contact with fresh cement, which is really almost impossible. If you're pouring concrete, it's going to be coming into contact with air. So that's really a process that starts almost immediately once you mix your concrete and start placing it. The relative humidity does need to be between about 40 and 90%. So if you're in, say, South Florida, where my business is headquartered, in the summertime, it's not so much of an issue because it's a swamp down there. It's so humid and hot and miserable. Nothing wants to be down there, not even corrosion. I always joke with the colleagues that work down there. I say even corrosion doesn't want to be here in the summer. It's so dang hot. But really high humidity is going to shut down the process, as is really low humidity. So if you're in the winter time when it's really cold and just really dry, that's also when corrosion tends to shut down as well, just because it's so cold and dry. You just don't get the activity that you would get in that more middle range of 40 to 90%. But what happens when carbonation starts happening, it reduces the porosity, as I said. So that actually will increase the strength of the cement paste because you have a more dense concrete, essentially. But it does, again, lead to that reduced alkalinity of the concrete, which would penetrate the passivation layer. So fully carbonated concrete, what we mean by fully carbonated concrete is essentially concrete where the carbonation is penetrated as far down as it's going to happen. It gets to some distance down into the concrete, and then it stops happening. So in the picture that you see here, what they did was just put some phenolphthalein solution on the concrete. You can see it reacts in the middle portion of that sample. So in that middle area where it's red, you don't have any carbonation happening. But at the surfaces where it's exposed to the air, that's where the carbonation has actually started to happen. So you get that lower pH. So you don't get the reaction of the phenolphthalein with that bright red color where it's a lower pH concrete. But again, by reducing that pH, carbonation is just accelerating the time to depassivation of the steel, which again will basically expose it to being able to start reacting with the chloride. So carbonation in and of itself, it's really not a bad thing. It's not causing deterioration of the concrete. It can lead to some corrosion of the reinforcing steel, but it's more of that like really widespread corrosion that maybe if when you're a kid, if you left your bike outside, maybe, for a couple of weeks and it was just out in that moist air, it starts to kind of rust all over the whole surface of the bike, but it's not like a real bad, penetrating, pitting type of corrosion. That's kind of typical of what we see from carbonation induced corrosion. So it's not not a big deal. It's not really a threat to the concrete. Whereas chlorides, when they react, that all happens at one isolated location, and we get what's called pitting of the reinforcement steel. So it's a much bigger problem as far as, detrimental to the strength, and structure of the concrete. So again, carbonation is just something that's going to happen, just something to be aware of. So when we're building new structures, we need to keep that in mind so that we can, use products that will kind of help delay the carbonation as much as possible, or extend that passivation layer as long as we can, keep moisture out. Again, all the different technologies that we're going to talk about, in the latter half of this presentation, are things that we need to be thinking about, even on a brand new structure, because as soon as you put that in place, as soon as the concrete is poured, it's going to be basically setting itself up to start corroding sometime in the near future. So chloride-induced corrosion, again, which is really, from here on out, that's really all we'll be talking about. And again, like if we were in a chemical plant or something, the process is really the same. It's just a different chemical and some different reactions as far as the chemical equations that we're going to see. But it's the same procedure. We're just going to be talking about chlorides because, frankly, in probably 95% of the cases, we're talking about chloride-induced corrosion when it comes to concrete. So I touched a little bit on the sources of the chlorides earlier, but just again to rehash that, there's really two sources. They can be internal sources or external sources. The internal sources can include things like the mixed water. So a lot of municipalities around the country actually do use chlorides to help treat water. So if you are getting your mixed water from the faucet, like you should be, there's a good chance that there's actually some chlorides in that water that you're using to mix your concrete. It's very, very common. Aggregates, another one that people may not think about, but where I live in Cleveland, we actually have a lot of aggregate. So there's ships that come in and out every day, and they leave filled with just piles and piles of rocks that's going to be used in various concrete mixes around the Midwest, essentially. But where they store all of those aggregates happen to be right below one of the major highway arteries that runs through Cleveland. So as you can imagine, in the wintertime, when we're getting all of our snow and they're dumping the road salt from the salt trucks and the cars are driving by, all of that salt and that water that's getting splashed off the bridge and leaking through the bridge and falling down, it's getting onto that aggregate that's sitting below, which is then getting shipped out by a big ship to wherever its final destination may be. But that's why it's always good in your specification to say that they should be using cleaned aggregate. You always want to wash off the aggregate before you use it. And that's mainly because you don't know where it's been stored. It could have been accumulating chlorides while it was sitting wherever it was. And those chlorides, if you introduce them right at the beginning, are going to just speed up the time until corrosion starts to actually happen. And then the third one isn't really an issue anymore, but admixtures back in the 60s and 70s, before we had a better understanding of chlorides and what they did, how they reacted with reinforcement steel and concrete and the problems that they caused. Chloride was actually used as an accelerant. So in the wintertime, when they were pouring concrete, they would use chloride as an admixture just to make the concrete cure faster. So it's very common when you go to older cities. Chicago is a good example. You can start looking at buildings and you can kind of tell which floors were built in some of these buildings from the big skyscrapers that were built in the 60s, 70s era. You'll see, every 3 or 4 floors or so, there'll be a lot of concrete repairs being done. Then the next 3 or 4 floors, you won't see any repairs being done. Then the next 3 or 4, it'll have a bunch of repairs and so on and so forth. Well, what was happening there was the floors that have a lot of repairs going on generally were the ones that were constructed in the wintertime when they were using chloride as an admixture. So we're still dealing with that, the fallout from that today. It's an ongoing problem. Those structures are just going to continue to corrode, and we'll have to continue to deal with that and provide solutions for those buildings as long as they're standing. But nowadays the ACI limits are very, very small. You're not allowed to use chloride as an accelerant. Even the amount of allowable chloride is so small, like that there's really, you just don't have to worry about it. As long as all the products, the mix design is meeting ACI requirements, it's going to have a very low chloride content as far as the admixtures go. However, then there's the external sources. which I mentioned, de-icing salts, precipitation, can help wash those salts as it rains. All the surface salts from the road salt starts getting washed into the, into the various bridges and roadways, what have you. And then I kind of, half jokingly put contractors there at the bottom. What I'm referring to there is, and this has happened, you get a contractor, maybe they're doing a parking garage along the coast or a bridge along the coast, whatever structure it may be, but they start to run out of water. They're looking at this big, nice ocean sitting there, and they say, you know what, let's just go grab a couple buckets of water out of the ocean and use that. Well, as you know, ocean water is, salt water. There's all sorts of chlorides in the ocean water. So it's a really bad idea. I would like to think that it's never happened, but knowing contractors and working with them as much as I do, I'm sure at some point it's certainly been done. So just the point is, make sure you know where your water is coming from. You don't want to just use any water when you're mixing concrete. It's important that you know where that water is coming from. Now this slide here, this was done by the National Atmospheric Institute, I believe it was called. But basically what they were doing was they were measuring airborne chlorides in various parts around the country. So this is again due to basically ocean winds blowing, off the ocean and into the coast. So a lot of times people will think, well, when we're talking coastal areas for corrosion, we're only talking those first few blocks, the $1 million homes right along the ocean. Those are really the only ones we need to worry about. But when you look at this chart here, you can see that that's really not true. So basically all of South Carolina, for example, is in the really high range of chloride content. Most of Georgia, certainly all the way up into the Atlanta area, is in really high, severe chloride concentration. So those winds blow that salt in the air from the ocean quite a ways. It's several hundred miles. So this could be a problem very far inland. Certainly it's not just limited to just a few miles off the coast. It's something that happens several hundred miles off the coast. You'll see, obviously, it's concentrated along the Gulf of Mexico and along the southeast. That's pretty typical. California, Oregon, and Washington State also have pretty high concentrations. As you can see, the difference out there is it's very dry. So I mentioned that humidity has a big part to play in corrosion. So the humidity in California is just very low. It's very dry and pleasant out there. Same with Washington and Oregon. So you just don't see as much of the corrosion actually happening simply because of the environmental conditions. It's just not ripe for corrosion out in those areas. So we don't generally see as much of a problem as you do on the East Coast. But the end result is the same, no matter where you are, once you get chlorides that start to infiltrate your concrete. So what happens is the iron gets converted to the iron oxide. We touched on that before. And when that happens, so iron oxide, or the rust that we call it, actually takes up about 4 to 10 times the volume of the original reinforcement steel. So it kind of expands, if you will, as the rust starts to form. It takes up more space, and by taking up more space, it starts to impart a tensile force on the concrete. As we know, concrete is very, very strong in compression, but it's just not very good in tension. That's why we use the reinforcement steel in the first place. So as you create those internal pressures in the concrete that creates that tensile force, that causes the concrete to crack because it's being overstressed. So it cracks to relieve itself, and then those cracks typically will lead to spalls down the road as the cracks kind of spread and take out a big chunk of concrete, and then you get that falling concrete problem that we're trying to avoid. So that's kind of the process, in a nutshell, in a simplified way. This is the actual chemical reactions that are happening. So I'm not going to spend, again, a ton of time here. This isn't this isn't a chemistry class. I'm not trying to put you all to sleep either. But there's a few things to just kind of take away from these reactions. So this is the full set of chemical reactions that occur when corrosion happens in concrete. So you start out, you have the iron and the chlorides reacting that form those iron chlorides, and simultaneously the iron is being oxidized and releasing electrons. And then you have water and air kind of reacting with those free electrons from the iron, which forms hydroxides, which then react with the iron to form iron hydroxides, which then react with the air and the water again to create those the iron oxides, or the rust that we're trying to avoid. So again, not going to test anybody on this, but there's just a couple of things to point out that are worth paying attention to. And really, that's that there's no net consumption of anything. So you have chloride as a reactant, and you have chloride as a product. You have air and water as a reactant, and you have air and water as a product as well. So the reason that's important is once the chlorides are there and once this process starts to actually happen, it's not like the chlorides get consumed. They're not being like eaten up by the reinforcement steel and going away. They just continue to congregate at the reinforcement steel, and the more chlorides you get, the faster these reactions happen because there's just more of it. It's like putting more wood on a fire. But unlike the fire, the wood, the chlorides don't burn away. They're going to always be there, and they're going to always provide fuel to this set of reactions. So it's not like we could just say, okay, well, it's been corroding for 15 years now, so all the chloride should be about used up. Now we don't have to worry about it anymore. Unfortunately, that's not how it works. You're going to have 15 years of chlorides that have accumulated, plus all the other additional chlorides that are continuing to accumulate. But more simply, without getting into the weeds of chemistry too much, really rebar plus chlorides and water, and really that should probably say air too, is equal to rust. That's how we get rust of reinforcement steel, is you have rebar, you have chlorides, water, and air, and all those things come together to create rust. So this is pretty typical of what we'll see with chloride-induced corrosion. And remember when I was talking about how the carbonation was a more widespread problem, it was over the whole length of the bar, but the chlorides was more of a pitting corrosion, what we call. So pitting all happens at one spot. So you can see at what we call the anode site, that bar is completely ruptured. So the corrosion was so severe at that one area that it actually ate through all of the reinforcement steel to the point that that bar actually rusted all the way through. But if we look just a few inches down the bar to the right, you have this cathode site. You can see you have perfectly clean steel there. There's no rust. Everything looks great. So that's pretty typical of what we see with chloride-induced corrosion. You're going to have a really bad area, and which is the anode site, and then you're going to have the side that's being reduced or accepting those free electrons, which we call the cathode site, and it's going to look like it's perfectly good, perfectly clean. So that's why we see these spalls happening in very small, isolated locations, because all the corrosion is happening in one small kind of isolated location. What's driving this is what we call the electromotive force. So if you kind of think of this as a waterfall, I know this slide's a little wordy, but if you kind of just think of corrosion as a waterfall, we're looking at the Niagara Falls here on the picture on the slide. Those are pretty big waterfalls. So there's a lot of potential from the top of that waterfall to the bottom because it's a really big drop. But if you're in more of your local park, and maybe you just had one after a big rainstorm, there's a little stream that forms. Maybe you get like a little, 2 or 3 foot waterfall. That little waterfall is going to be much lower potential. So corrosion is really the same way. The more chlorides you have, and the bigger difference between the cathode area and the anode area, the difference in potential between those two areas, the greater that is, basically the faster the corrosion is going to happen. So that's the gist of what we're talking about here. It's EMF is electromotive force, that's voltage. So again, we generate electricity out of hydro plants. It's the same concept. You're using that force of that water as it falls to generate electricity. With corrosion, you have chlorides accumulating, and they start generating a current. The more that you get, the more and more that you get, the greater and greater that current gets. And the greater that current gets, the greater the rate of corrosion that we see in the reinforcement steel. So that becomes important as to, how fast is the structure deteriorating. It's really going to depend on, on these potential differences. So I'm not sure why that slide got tucked in there, but now we're going to get into how do we solve this problem, or what can we do to fix this? We're not defenseless. As I mentioned, it's something that just kind of happens, and there's nothing we can do about that. But there are things that we can do to kind of mitigate the effects and the negative consequences of corrosion. And what I like to think of this as breaking the chain. So if you remember those equations that I showed you that I just said, don't worry about, we don't need to remember them, and you don't. But if you just at least for a moment remember those, if we take any one of those components away, if we take away the anode or the cathode, or we remove the electrolyte, which is basically the water in the concrete, or if we remove the chlorides, or we take a high pH and make it a high pH, if we do any one of those things, we're going to break that chain of corrosion. That whole set of equations, those chemical reactions that I showed you, those can't happen unless all of those items are there. So if we remove just one of them, then we can stop the whole process from happening. So with all of the products that are out there on the market for corrosion in concrete, they all generally attack one of these four things. They're going to go after either the anode or the cathode to prevent the reinforcement steel to actually function as an anode. You can go after the electrolyte, which is basically waterproofing. You're trying to keep moisture out of the concrete. If there's no moisture, there's no electrolyte. If there's no electrolyte, then again, those equations that series of reactions won't happen. They simply can't happen. The same is true of chlorides. So if we can remove the chlorides, physically remove them, which you actually can do, it's very expensive, but you can physically remove chlorides from concrete. It's called chloride extraction. It's very time consuming. It's not good for bridges because you've got to shut down the structure for probably at least a month minimum to set up the system, but it can be done. And then the other thing that you can also do is just raise the concentration required for corrosion. So remember, we said there was that the parts per million, about 330 parts per million, the chloride concentration limit for the passivation layer. What we can actually do is add materials to the concrete mix or the repair mix that raises that concentration. So we can get up to, say, maybe 500 or 600 parts per million and just delay the process a little further. Now, that also assumes, of course, that you're keeping the pH above 10, because we said also if you get below that 10 and a half, that the chloride will also start to react. So it's kind of a, just a belt and suspenders kind of slow you down type approach, but not a permanent fix. And then you can, of course, raise the pH as well. So there's products that you can add, posthumously, if you will, to concrete that can kind of raise the pH. So there's some chemical treatments out there that would do that. And then again, the idea there is to just reinstate the passivation layer, similar to what we were doing with the admixtures for the repair mortars. So what we'll do is just going to kind of go through all the different technologies that we at MAPEI have. And again, these are also what we at MAPEI have are very similar to what everyone else in this industry has as well. So there's nothing really here that isn't also everywhere else, but we'll just kind of go through some of those technologies so you have an idea of what they are and how they work and how to try and select which is best for your particular project. So the first is just concrete admixtures. So these are just additives that are added to the original mix. This could be a ready mix for a new construction. It could be a bagged product. So MAPEI, we sell bagged repair mortars. We add them to most of our repair mortars as part of the mix. And the idea is to basically just delay corrosion. It's not going to prevent corrosion. It's certainly not a preventative measure. We're just delaying it. Generally, calcium nitrite is what is added to the bag or the mix. That's pretty typical. It's the most effective. That's what everyone is pretty much using across the board. But when you add calcium nitrite to the mix, basically all that it does is increases that threshold. So that 330 parts per million, it raises it up to, say, 500, 600, 1,000, whatever. It's going to depend how much calcium nitrite you add, how much it raises it by. But again, you're hoping to just delay corrosion as long as possible. So the longer you can delay it, the longer theoretically the life of that structure would be. The other one that gets used is what we call SCMs. These are supplementary cementitious materials. It's kind of a mouthful. So I'm just going to go with SCM. But this is silica fume, fly ash, those types of things that are just being used to basically increase the density of the concrete. By increasing the density of the concrete, you're just keeping chlorides out, you're keeping water out. You're just, again, it's just trying to slow things down. So the effectiveness of these products, they're very effective as far as delaying corrosion. SCMs will certainly slow the diffusion rate as well, but it's not going to prevent subsidence cracks from forming. And once you get cracking, you're going to get more moisture intrusion, and the whole process is just going to be, it's delaying the inevitable, essentially. So it's a good, cheap thing that should always be added to really any concrete, just because it is going to slow things down, but it's not going to prevent corrosion in the long haul. Then there's alternative rebar. So this could be this could be your epoxy coated bar, your FRP bars. Basically, it's putting something around the reinforcement steel or using a non-corroding material for the reinforcement in order to basically prevent corrosion. So again, this could be epoxy coated stainless steel. Then there's the carbon and the fiberglass bars, the FRP bars. Those just don't corrode at all. Epoxy coated bars, it's kind of a contentious one. Some people are firm believers in epoxy coated bars. I happen to be in the camp that's not a big believer in them. I just feel by the time they get out to the job site, there's going to be plenty of pinholes from transportation damage and being lifted off the truck and dropped on the ground and everything else. It's really impossible to say that the bar is completely coated. And if you have even one small hole, as we talked about before, those chlorides are going to all matriculate to that one small hole and really attack the steel all at that one location, which is going to be really bad in the long run. So not a big fan of it myself, but I'll freely admit it is widely used as a preventative measure in the concrete industry, particularly a lot of the DOTs. So it's something that you definitely will see. Stainless steel, not so much, just because it's very, very expensive. And it's not a permanent thing. It's just, again, slowing things down. So, you're not going to come across the stainless quite as often. You are seeing a lot more carbon and fiberglass FRP bars being used, but there's ductility issues with FRP. So we're not quite ready to start just using them in lieu of steel at this point in time. I think more research needs to be done before that can happen. And the codes do prevent you from doing so currently. As far as the effectiveness, these systems, they are extremely effective. I mean, FRP bars simply will not corrode. So if you're using carbon or fiberglass, that you don't have to worry about corrosion. It's simply just not going to happen. With epoxy coated bars and stainless steel, I mentioned the issues with the epoxy coated bars. Stainless, it's more just slowing it down. So they're varying degrees of effectiveness. The epoxy coated bar, if it was done perfectly and it had no pinholes and no exposure whatsoever, it would certainly be very good. But again, over time, it's probably going to deteriorate anyhow, and you're going to at some point probably get corrosion. So these more fall into the category of delaying more than preventing. Then there's waterproofing. So this is a really simple thing that frankly should be done on any concrete structure. Certainly if it's going to have chloride exposure, it's a really good idea. But all you're really doing is you're providing a barrier against water and chlorides that get into the water from catching a ride, if you will, down to the reinforcement steel with the water. Great preventative measure. As we talked about, if you remove any one of those items from those series of equations, you're going to stop corrosion. Well, if you can keep all of the water out and you keep your structure dry from the time that it was built until the time that you don't need it anymore, you'll never get corrosion. So if you're constantly staying up with your waterproofing, you're going to keep corrosion pretty limited. Now, you're going to always get cracks and things are going to happen. So water is going to get in. It's not something you can totally prevent. But doing regular waterproofing, certainly in like a parking garage type of structure, is a really good idea. Really should be done with more regularity than it is now. I think it would save the owners a lot of money. Bridge decks too. There's ways of putting silanes and different things down on the surface of bridge decks that will work to varying degrees to keep water out of that. So I mean, you have basically, it's pretty typical. You have like your 20% silane, 40% silane, 100% silane. Those are those Planaceo products down at the bottom, the WR, and then WR40 and WR100. You can figure out pretty easily which is which. And like something like the MAPEI floor system, that's a urethane deck coating that you would see. It's like the gray paint that you see in parking garages all the time. So those urethane systems are really good for maintaining parking structures. Don't see it on bridge decks as much just because the amount of traffic that they see, it just wouldn't hold up very well. So it's more typical to use the silanes on a bridge deck. But really, it could be a deck membrane, just a high build coating. FRP liners are used, sealers. Any type of material that's going to keep water out of that concrete is going to be very effective to at least delay corrosion to some extent. It's just going to push it back. The longer you can keep pushing it back, the longer until you have to start doing costly and expensive repairs to that concrete. Then there's removal and replacement of contaminated concrete. So this is, pretty typical. What happens, maybe a motorist calls in or something and they say, hey, I was driving down the highway, I hit this giant pothole and it, bent my rim or whatever might have happened. So the DOT goes out and investigates and they see, oh yeah, we've got some spalling happening on this bridge deck. We need to address that. So what they'll do typically is they'll just cut out a square area. Hopefully it should always be square. You don't want to be doing, little art projects on your bridge deck. Concrete should always be patched in square patches. But they'll basically cut out, they'll tap with a hammer or do a chain drag on the deck and figure out where the loose concrete is at, or, just by hearing those void sounds. You hear a change in sound, you've got some loose concrete. They'll remove it and then patch it. And there's all sorts of different repair products out there that you can be used. And we talked about how most of them will have a corrosion inhibitor added to them. And they'll go ahead and just patch that bad area up and then they'll leave. So they've removed the bad area. Everything seems to be pretty good shape. So they leave, they go home. They think everything's great. The problem with this procedure is that it does not consider something that we call the incipient anode effect, or sometimes called the halo effect. But whether you call it the incipient anode effect, the halo effect, there's probably other names as well. The result is the same. So if you remember, we were talking about when I had that waterfall slide up there, and I was talking about how the different potential, if you have a really big drop in potential, you can get a lot of energy out of that. That's basically the same thing that's happening with patch repairs like we just looked at. So basically what happened is you have this existing bridge deck and it's been sitting there for 30, 40 years. It's been, absorbing chlorides for all that time. So the whole bridge deck is very high in chloride, just from being in use over the years. But now you've went and you've replaced this really small patch area. And so that really small patch area is very, very low in chloride content. It's very low potential. There's not going to be corrosion happening in that area because the steel is going to repassivate from the high pH. You have the low corrosion, the low chloride concentration as well, will also help repassivation of the steel. But you're going to have all that happening, and it's going to be immediately adjacent to really high potential concrete on all four sides of it that does not have the protection of the passivation layer anymore because the chloride concentration is really high. The pH has dropped. So basically, once you put that patch in there, you basically just you reverse the process. So what happens is we'll call it chasing the repair. So you do this repair area, and then 2 or 3 years later, you'll get the call, and they'll say, "Hey, you did that patch, but now it's just corroding all around the patch. It's just all cracking and falling apart. What's going on?" Well, what's going on is we've created this big giant drop in potential between the repair area and the existing area, and that's ripe for creating a new corrosion cell immediately outside of the patch. So we call that chasing the repair. This is pretty typical to see. I mean, it's a little tough to see on the picture, but some of these lighter areas that you can see. Hopefully you can see that pointer, the mouse pointer. But there's the lighter areas of concrete. You can see little rectangle patches that have been done. So they probably started here in the end. They did this first, and then they came back a year later and they said, hey, it's starting to fail here now. And then it moved over to here, and then, up over to here. And you can do this, you'll as a contractor, you'll love it because they keep calling you every 2 years, 3 years to come back and do more work. But as an owner, this will drive you nuts. You don't want to keep having this problem over and over again. Just constantly chasing the repair down the whole length of your deck or your bridge, whatever it may be. So this is obviously something we want to avoid. So we do have the technology to do that. They're called sacrificial galvanic anodes. They're generally a sacrificial metal core of some kind, generally zinc, that are encased in a cementitious matrix of some sort. They're all manufacturer specific, so they all have their own little special sauce in them. They're supposed to do different things. But the idea is by putting a piece of zinc and attaching it to the metal, the iron, zinc is going to preferentially corrode in the presence of iron. So all the corrosion, instead of happening around the patch like it was before, is going to happen in that zinc anode. And if you have an anode with a, say, 10 to 15 year service life, the thought is by the time that anode fully consumes itself, the concrete that it's in will have absorbed some chlorides. It will have dropped in pH. It'll be more at a balanced state with all of the concrete around it. And then you don't get that chasing the repair situation. So very, very, very effective. They definitely work. There's plenty of science out there that proves that it works. Really, any kind of concrete patch that you're doing, it's a really good idea. Excuse me, really good idea to use zinc anodes. There's also different forms. There's zinc-rich coatings that you can use as well, and even just rebar coatings that prevent the steel in the patch area from acting as the cathode in the reaction work as well. So really should always be doing something along those lines in a patch. But how they work is they basically turn that anodic reinforcement steel into the cathode. That forces the electrons to flow toward the steel and not away from it. So if you remember, the corrosion happens where the electrons are leaving, not where they're going to. So we want the electrons to be going to the reinforcement steel, not being pulled away from it. Then we also have the electromotive series that I mentioned before when we were talking about the waterfall. But zinc is basically less noble than steel. Any metal that's less noble than another metal is going to corrode in the presence of that other metal preferentially. So that's why we use zinc in the anodes. You could use aluminum, which is a lot more expensive than zinc, to be honest. That's why we're using zinc. But you basically are just putting a material there that's going to corrode instead of the reinforcement steel. So when we go back to this image, instead of the repair area turning in, into the cathode and then creating an anodic area around the exterior, you're keeping the anode inside of the patch in that, in that galvanic anode, and then the steel on the outside of the patch remains cathodic, continues to accept those electrons, and it does not corrode, and then you don't get that cracking and spalling immediately around the patch area. So a really good idea. They're not very expensive relative to the savings that you get out of using them. But it's pretty typical. You'll attach them. They'll have two like metal wires of some sort sticking out of them. Then you'll make sure you get good electrical contact with the reinforcement bar, and then strap it to the bar to make sure it stays in place. They should always be done around the edge of the repair because that's where the big potential difference is happening. So if it's a really big 10-foot by 10-foot patch, you don't really need them in the middle of that 10-foot by 10-foot square. You really just need it around the perimeter typically. The MAPEI anodes, they use just a big zinc plate folded on itself like you see here. Then there's a hydrophilic paste, cementitious paste that kind of is placed around the exterior of the plate. As the hydrophilic paste comes in contact with the water and say the patching mortar that you're pouring around it, it starts to slightly expand just a little bit, which leaves room for the formation of those zinc oxides that are going to form when the corrosion starts happening. So you don't get the cracking from expansion of the anode like you would with cracking of the reinforcement steel. They do use a chloride activator. So some of the specs you'll see, there's one competitor. All the anodes on the market use chloride activators except for one. And that competitor is very aggressive with their specs. So they'll have a lot of specs that say, you know, you can't have any chloride or any deleterious material to concrete. Folks, we're talking about adding like a pinch of salt to the ocean is essentially the amount of chloride you're using. It's not a big deal. Everybody's anodes, frankly, are doing it. It's not going to leach out into your concrete. It's not going to cause, you know, more corrosion in your deck. It's all going to be confined to this anode for as long as it's there. So it's really not a big deal. You have to use something to cause the anode to start, basically to turn it on, to flip the switch to on, if you will. So that one manufacturer that doesn't use chlorides uses pH. You have to be at like a pH of 13.5 or higher to get their anode to turn on. And what we have found in testing is that you can't maintain that high of a pH. The second you open the anode and expose it to air, it starts dropping down, you know, almost immediately. So what we found is those anodes never turn on. They just stay passive, and you may as well not even put them into the patch. So they just don't work very well. That's why everyone else is using chlorides, because we know that they work. But yeah, there's different sizes of anodes. 70 grams, 105 grams are pretty typical of what you see. There's some bigger ones too, you can see there as well. Basically, the more zinc you have, the longer it takes to consume all of that zinc. So if you want it to last a really long time, you use one of the really big ones. If you're just looking to maybe get a couple of years, you can use some of the smaller ones. And then, of course, there's everything in between available to you as well. There's also the coatings that I mentioned. So there's cement-based, there's also epoxy-based coatings. The idea with the coatings is the same as the anode, really. You're just preventing that cell from the anode cathode cell from forming by putting a coating around the steel. They work really well just so long as you completely coat the steel. It's the same as epoxy coated bars. If you don't completely coat it front and back on all sides and every little nook and cranny, it's not going to work. So you've got to make sure that you coat the entire thing completely. There's plural component, typically the epoxy ones, and then single components are the cementitious ones. But again, they work really well as long as you completely encapsulate all of the bars. Then lastly, so we're kind of getting up against the end of the hour here, but we're coming to the end anyhow. We have our surface applied inhibitors. So traditionally, these were just amino alcohol-based products that really they need to get to the reinforcement steel. If you can apply it directly to the steel, it would work great. But typically how they're used is you put it on the surface of the concrete, and then you're hoping that it kind of works its way down to the reinforcement steel. This product was actually initially developed by 3M Corporation back in the 80s when I don't know I'm not sure how old everyone is on the call, but if you remember the Sony Walkmans and the big electronics boom in the 80s, all the radios and stuff, you know, all those electronics were coming from Vietnam, Korea, or, you know, over the oceans, where there's, as we've already mentioned, there's a lot of airborne salts in the ocean. So what the electronics manufacturers were finding was they'd order a container full of components, and then those components would show up in America, and they would just be all corroded and shot, you know, basically useless because of all the corrosion. So 3M developed this amino alcohol product, basically to just spray all over all these electronics as they went across the ocean to prevent that corrosion. We realized that we could use that same concept with reinforcement steel and concrete and started doing the same thing. So, you know, does it work? It works very, very well, only if it gets to the reinforcement steel. And that's an if. That's a big if. And the unfortunate thing is there's really no way of knowing. You can't just do like a core test and cheaply and quickly determine if the product has actually gotten to the reinforcement steel. So we're not seeing these products used as much anymore. More common nowadays is these, what we call dual component inhibitor. Basically, they just took that same product we were talking about before, and they added a silane to it to give it some waterproof or water repellency. And then you can actually do a core test, and you can take a core of the concrete, see how far the silane has gotten down. And then you can correlate that. Okay, if the silane got 2 inches, we know that the amino alcohol got 4 inches through some third-party testing that's been done previously. So you can actually get a visual representation that, okay, yeah, I know that it actually physically got to the steel. So the engineers just tend to be liking these products a little bit more just because of that. But both work just as well, assuming they get to the steel. But the advantage of the dual component is you can kind of easily test to see that it did in fact get to the steel. So with that, we have about 5 minutes or so left for some questions that I'd be happy to answer. And any that we don't get to, I will follow up via email afterwards. Thank you.
Wow. Thank you very much for that presentation. That was excellent. Brian, as always, MAPEI just has great information, and the webinars that come from you guys are awesome. Let's look and see what we have here in terms of questions. I think we only have time for one. And I'm going to go with Christian Cooper, who asks, are galvanized bars an option?
Yes, galvanized steel certainly is an option. It's used more commonly with like big plates, like gusset plates and things on bridges. But you certainly could galvanize reinforcing steel. It's just pretty expensive. It's probably a higher cost than epoxy coating, so it's not used as often as epoxy coating. But yeah, absolutely, galvanized bars are going to be an option for reducing corrosion of reinforcement steel, certainly.
Okay, well, I wish we had time for more, but unfortunately we've come to the close. That wraps up our questions and this webinar. Any questions we did not get to, we will answer offline. On behalf of Roads and Bridges Media and our sponsor, MAPEI, I would like to thank everyone for their participation and for staying engaged. This webinar will soon be archived at the same URL you used today and can be viewed on demand, so feel free to share it with others. Until next time, I'm Gavin Jenkins with Roads and Bridges. Stay tuned, and we'll be back with another webinar soon.